really long.
Next page is how we do those.
Wait, really?
What it says on hers.
Okay. It appears Elmo has its act together now. I have no idea what just happened. Okay. Lesson 43 is what we are attempting to get into now. Okay. Area under a curve as an infinite summation. So a couple of lessons ago, we started off with area under a curve and we were making rectangles, yes? And we would make a set number of rectangles. Like it would tell us make 4 rectangles. We would add up those areas. Now, that is an estimate, okay? That's not an exact answer, okay? It is an estimate, and depending on if your rectangles are smaller than the curve or bigger than the curve, it's either a small estimate or a too big estimate. So today, we learn the next method, which is area under a curve as an infinite summation. And this will find our precise answer. Okay, this is going to be a precise answer. It's not going to be our easiest method to finding the precise answer, but it does find the precise exact answer. So, you will notice, it's already been pointed out, steps are on the next page. So I'll be talking about those steps on the next page. They kind of, will take you through what you need to be looking at. So let's look at example 1. It says to use inscribed rectangles to find the exact area. So notice it used the word exact. Under y equals 2x on the interval 0 to 2 by allowing the number of rectangles to increase without bound. Meaning there's an infinite number of rectangles. And as there's an infinite number of rectangles, the rectangles are getting smaller and smaller, and they're fitting more precisely under the curve. That's the idea of how this works. Okay, so inscribed rectangles. When we talk about inscribed rectangles, we're talking about rectangles that are under the curve. So when you see that word inscribed, I would think of it as lower rectangles because they are rectangles that are under the curve. We'll talk about the opposite down on the other example. Our curve here is y equals 2x, and we're on the interval 0 to 2. So, if you have flipped to the next page, step 1 is to draw a sketch of the curve with the correct type of rectangles underneath. Remember, this is just a sketch. My sketches are going to look similar to what we did last week. I'm going to make them big enough so that we can see what's going on here. There is lots of work on these, so make sure you leave yourself room to do lots of work. What does y equals 2x look like? Yeah, okay, it's a steeper line than y equals x. It is just a line, though, and it goes through the origin. So there's mine. Okay, there's my x-axis, my y-axis. There's my y equals 2x line. And it said on the interval from 0 to 2. So I'm going to put my 2 over here towards the right. I don't really have to have a 1 in there for this. There's y equals 2x. 0 to 2 means I'm going over to that point. And it says, it's inscribed rectangles, and they are, so inscribed I said is lower. They're inside. So first of all, what I'm going to do is I'm going to break this into intervals. And I'm not going to break it all up. But like the first one I'm going to call this x1, this first line. The next line I'm going to call x2. Remember, it is the rectangles are increasing without bound. So obviously there's going to be a lot more than 4. And there's going to be a lot more than like the 8 I'm on track to draw or something. And then, what I'm going to do, so this 2 right here is the end of our nth rectangle. So this 2, I'm going to call x of n, because it is the final spot. Okay? But I'm also going to draw the rectangle before it. So if that last one, the 2, is represented as x to the n, what comes right before x to the n? X to the n minus 1. And I'm going to draw that one in as well. The idea is there's more rectangles in there, right? I didn't draw all the rectangles. This is just the idea of getting us started because we kind of need the picture to help us get going here.
Does it matter that my gap was no longer?
No. Doesn't matter at all. Now, and if I recall, it told us to go ahead and the correct type of rectangles. So we said they are lower, yes? So lower means which side am I going to be drawing these rectangles from? The left, essentially, because if I draw that one there, it goes from x of n minus 1. We're going to have one that goes from the top of x3 to x4, one that goes from the top of x2 over to x3, the top of x1 over to x2, and this last one goes from 0 over to x1. And again, it's because it's a lower rectangle, or inscribed rectangle. Okay, so this is our drawing. Again, the end interval is always the nth rectangle, which makes the one before the n minus 1. Okay, so we drew the sketch of the curve, correct type of rectangles. Step 2, we're going to talk about delta x. And in order to find delta x is b minus a over n, where b and a are the ends of the interval, and n in this case is just n. It used to be that n was the number of rectangles. We don't have a number of rectangles, so n is just n. So, let's see, I'm going to do this right up here. Delta x, b minus a, so my b minus a is going to be 2 minus 0 divided by n. 2 minus 0 divided by n is 2 over n. That is my delta x, and I will also tell you that is going to be what we use for the width of each rectangle. Okay. Step 3. Generally speaking, it says determine if the endpoints are left or right. We're actually going to set up, I think it's in this step that I usually set up my table. Yeah, because step 4 is set up the formula. So we're going to kind of set up the table that's going to lead us into our formula. So are my endpoints left endpoints or right endpoints? Left? Because they are always on the left-hand side of an interval, yes? Okay, so when we think, I'm just writing it up here so we can, there's physical evidence that we talked about it, right? Okay, they're left endpoints. If you notice on that next page, it talks about if they're left endpoints versus if they are right endpoints. When you look at the next page. And it says, if left, we begin with 0 delta x and end with n minus 1. If right, we begin with 1 delta x and end with n delta x. And n is always the end of our interval. So right here, and this is part of the reason we labeled it so nicely, because they're left endpoints, my first, because when I drew the lower or the inscribed portions, my endpoints go from the left to the right. The left side is what's on the curve. Does that make sense? Okay. So, because they're left endpoints, my first endpoint is 0. 1, 2, 3, 4, so on and so forth. Where's my last endpoint? And it's not going to be at n, it's going to be at n minus 1. Okay, so anytime they're left endpoints, you'll go from 0 will always be your first one, n minus 1 will always be your last one. And we'll do a right endpoint. So I'm going to set up a chart here. And what this chart is going to help me do is it's going to help me find, if you think about it, we had to have the width of each rectangle times the height of each rectangle, yes? And the width we already found. That's the delta x. Do you remember how we found the height of rectangles on the last lesson like this? What do we do to find the heights? We had to take our x values and put them in the equation here, right? But we're not using 1, 2, so on and so forth. So let me set it up and show you what. The first interval we just talked about begins with 0. Then I have an interval that begins at 1, at 2, at 3, and so on and so forth. I'm going to actually just ... What is the last interval I have to use? N minus 1. So my I values are those subscripts. So the fact that we go from 0 to n minus 1. Again, if it was right, we'd change that up slightly. But since they're left endpoints, it's 0 to n minus 1. What we need to find is what I'm going to call x of I. And this x of I is what we will use to plug into our equation. Now, it'll probably be helpful if I tell you what x of I is just taking your I value, and multiplying by delta x. So the I value being the interval number, so to speak, times delta x. What is our delta x on this problem? 2 over n. So I is 0. 0 times 2 over n is 0. Just going to put 0 on that one. I'll write it out more as I get into them. On the next one, it's 1. My I value is 1 times delta x, which is 2 over n. 1 times 2 over n is 2 over n. My next I value is 2. So now I'm going to be doing 2 times 2 over n. What is 2 times 2 over n? 4 over n. And if you want it, I wrote out a little bit of work there. Just, it was 2 times 2 over n. My next one that I have written down is I value of 3. So that means 3 times 2 over n, which is 6 over n. ... We don't need all of these. We just need a handful to get us started. Okay? You'll see how it all works out in a moment. The last one we end up with is n minus 1 times 2 over n. So if we do n minus 1 times 2 over n. You could put it as 2n minus 2 over n, or actually, what I will probably leave it as, is 2 parentheses n minus 1 over n. So I'm not going to distribute it. And there's a reason I'm not distributing it. I want you to be able to see something later on. Okay? The third column, so the first column was our I values, just kind of numbering our intervals. Here are my x values. And the third column is plugging those x values in. So I'm going to list it as f of x sub I. But what that means is we're taking our x sub I numbers, which we just found in our last column, and we're plugging them into the function. What is my function in this problem? Y equals 2x. And so this column, sorry, my pen bounced away from me. This column right here is going to be the heights, because this is going to be what we get when we plug our x values in. So, the first one, it's 2 times x. X is 0. 2 times 0 is 0. Okay. The next we're plugging in is 2 over n. So 2 times 2 over n. 4 over n. I need to zoom in a little bit for this so you guys can see what all I'm writing here. Okay. Okay, 2x. The next one I'm plugging in is 4 over n. So 2 times 4 over n is 8 over n. The next one I'm plugging in is 6 over n. So 2 times 6 over n is 12 over n. Dot, 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 right? Just trying to get us a handful. This next one we're doing 2 times 2 times n minus 1 over n. And what I'll do there, again, I don't want to distribute it, but you can go ahead and do the 2 times 2 is 4. So I'm going to say 4, parentheses, n minus 1, all over n. Okay. The reason I did that chart is just so you guys can see where the values are coming from, so you have some organization to this problem. But that was all part of, it was setting us up for the formula, I guess. So it's kind of in between step 3 and step 4. They were left endpoints, so we set that all up. Step 4 is set up the formula. And just like how we did these when we had a set number of rectangles, it's the width of each rectangle times the height of each rectangle. Now, generally speaking, remember what we did is we put that width out front, and then we'd add up all the heights, right? So we didn't have to do width times height, width times height, width times height, and add those all up. So we're going to do that same thing. Now, if you're looking at the note, the steps, it says delta x. Delta x is always your width times the sum of the heights. And it's not going to make much sense right now. It says the sum of the heights is the equation with each delta x plugged into it. So, okay. The sum we're trying to figure out right here, this is the sum of lower rectangles. Okay.
It's going to take up a lot more room.
I don't know. I squished to get mine in. I mean, I have, right there's the edge of my paper, so I don't have a ton of room. I maybe have a little bit more than you do, yeah, but just write small and take up more lines than one if you need to. Okay, so it said to do delta x. So what's my delta x? 2 over n times the sum of the heights. Where do we find the heights? That's my f of x sub I. So the 0 plus 4 over n plus 8 over n plus 12 over n plus dot, 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 dot plus this. And so what I'm going to write out right here is those added. So it's 0 plus 4 over n plus 8 over n plus 12 over n dot, dot, dot plus 4 n minus 1 over n. Okay, so what we just did there, we did delta x, which was the 2 over n, right? And then what is this stuff in parentheses? This is the sum of the heights. Okay? That's your pieces there. Step 5 says factor out anything the sum has in common. And this is an incredibly important step. So first of all, we already have a 2 over n out front, yes? Okay. Ignore the 0 because we can factor anything we want out of 0. What do all of these have in common here? A 4 on top and an n on bottom, yes? So we are going to factor out a 4 over n. So I already have my 2n out front, 2 over n. Now I'm factoring out a 4 over n. I could probably zoom in more on this part now. So you have 0 and you take a 4 over n out, you still have 0. You have 4 over n, you take a 4 over n out, you now have 1. You had 8 over n. You factor out a 4 over n, you now have, no, the n's gone. We take out the n, 8 divided by 4 is 2, we're left with 2. You had 12 over n, you factor out 4 over n, we're left with 3, plus, dot, 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 plus. Last term, I take the 4 over n out, I'm left with n minus 1. Step 6. Replace the sum with one of the following. So this goes back, I'm trying to think if you guys maybe saw this in geometry, I'm not sure. But if you have a sum of numbers that is 1 plus 2 plus 3 plus so on and so forth up to n, that is represented by the expression n times n plus 1 over 2. If it was squares, which we'll see some squares, 1 squared plus 2 squared plus 3 squared up to n squared is represented by this expression. Cubes are listed by this expression. Now, what is ours similar to? The first one. I say similar because, is it slightly different? Okay. This one on the steps page goes from 1 to n. Our page right here goes from 0 to n minus 1. So we're going to have to tweak it slightly is what's happening because we are 1 off. And so what I'm going to write here, this is kind of a side note. If 1 plus 2 plus 3 dot 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 to n, if that normally equals n plus 1 over 2. That's what that normally equals, right? We're doing 0 plus 1 plus 2, so on and so forth, and we're going to n minus 1. The easiest way I can explain this. This one goes to n's. You see n's in here, yes? Ours goes to n minus 1's. Every place you see an n, replace it with n minus 1. So right here, my normal expression says n. Instead of n, I'm going to write n minus 1. This normal expression says n plus 1. Instead of n, it's going to be n minus 1. But what's n minus 1 plus 1? N. And then it's still all over 2. So because ours is slightly different, we're going to use that right there. Basically, if it was right endpoints and it went to 1 to n, we would use the given. So, we're going to replace now. Look back up at my last pink step I had. 2 over n stays 2 over n. 4 over n stays 0 plus 1 plus 2 up to n minus 1 becomes n minus 1 times n all over 2. And now, let's clean it up. Can I cancel some first before I clean up? 2 on top can cancel with 2 on bottom. And n on bottom can cancel with an n on top. And it's not that you have to cancel it, clean it up right there. We could multiply it all out and it would work out just the same. I do. I'm going to take the quiz. You can put that over on the cabinet. Do you need a pass?
No.
Thank you. Okay, so what remains? I have 4 n minus 1 all over n. Or if you prefer, 4n minus 4 all over n. Right? I can. So if you'd prefer to say 4n minus 4 over n, we can. Might help you see the last step a little bit easier. Because we are finally at the last step.
Oh,
And I thought I'd live to see the day.
7. Take the limit as n approaches infinity. So, this expression we just found here, yes? Okay, so
Wait, no,
it's not a ton of space you have to have left, okay? So, in order to find the area, this is how you find the area. You take the limit as n approaches infinity. I forgot to talk about limit notation on that test you guys looked at yesterday. So the limit as n approaches infinity of this expression right here, which is 4n minus 4 over n.